Over the past 6 weeks, I've developed and tested a method for accessible, low-cost monitoring and classification of obstructive sleep apnea. So the first question is, what is obstructive sleep apnea? Obstructive sleep apnea, or OSA, refers to when relaxing of the throat during sleep causes a blockage that reduces or stops airflow entirely. Approximately 20% of adults in the United States have OSA, of whom 90% are undiagnosed. During OSA events, reduced airflow results in a lack of oxygen supply to the brain, pulling you out of deep sleep. This can occur every minute in extreme cases, completely disrupting your sleep and making you feel tired or exhausted the next day. Untreated OSA can lead to an increased risk of coronary heart disease, stroke, hypertension, and cardiovascular disease. Currently, the gold standard for diagnosing sleep apnea and other sleep disorders is polysomnography, which involves a wide variety of different tests. For the millions of people who aren't even sure they have OSA, polysomnography isn't a particularly accessible or comfortable method of checking. Some sleep clinics do provide equipment which you can take home to record yourself with, but this generally isn't cheap. There's need for a widely accessible, low-cost method of self-recording and classification. For this project, I worked with a smartphone microphone, collar-clipped motion sensors, and a wireless pulse oximeter. The pulse oximeter monitored blood oxygen saturation, which was ideal for detecting difficulty breathing. By the end of the first week, I had modified some provided sample code to record motion data and audio simultaneously. And by the end of the second, I had almost entirely finished developing my own app for connecting to and recording from all three sensors. Up until this project began, I had only briefly meddled with Android app development, so it took a while to understand the flow and structure of working in Android Studio. The user interface needed to be unambiguous and intuitive enough that anyone could use it. By the fourth week, I was ready to begin recording some real data, but in the time available it was a challenge to find suitable candidates. We needed volunteers who had been diagnosed with OSA but had yet to begin treatment. And we were lucky enough to find one severely apneic candidate who provided us with 4 nights of recordings. In addition to their data, we also recorded 2 nights from 2 healthy, non-snoring subjects. Difficulties with the Bluetooth motion sensors meant that I wasn't able to collect enough chest movement data to do much analysis with. Unfortunately, I had spent quite a lot of my time in the previous week developing a method for calculating respiration rate from chest oscillation, which I had expected would be a useful metric for the OSA classification, so that set things back a little. My supervisor for this project was Professor Guy Brown, head of the University of Sheffield Department of Computer Science. He had previously worked on an audio classifier for identifying snoring sounds during sleep. To do so, they had built up a large database of audio recordings, from which I sampled 4 nights of different healthy snorers in order to round out my dataset a little, and to make things more representative of the population. There are various types of classifiers that one can use when attempting to separate data into different groups, but we chose to train binary decision trees in order to visualize the choices made. I trained decision trees on different combinations of the data in order to evaluate the sensor's effectiveness both individually and when used together. So how much potential is there for diagnosing OSA just using these methods? If you were to look only at the results, quite a lot. However, all but one of these experiments were trained against data from only 3 people. Only the apneic subject snored, which made the data extremely simple to separate. In the real world, 45% of the population snore at least occasionally, and this makes separation significantly more complicated. You can see this from the reduced accuracy of the decision tree which included the healthy snoring audio. That being said, this project demonstrated that OSA data can be effectively collected using smartphones and wearable devices. Over the past 6 weeks, I have successfully developed software that can now be used to record a larger number of participants and to train classifiers from their data. With more subjects, the methods developed here have the potential to provide valid conclusions as to the effectiveness of smartphone audio and pulse oximetry in classifying obstructive sleep apnea. Many thanks to Professor Guy Brown for his invaluable support and supervision, and thanks to my friends and family for their insight and help with writing my full report on this research. Thank you for watching, and I'll see you next time.